We'll accept those. Second? Whoever, Sarah, we'll have Sarah. Any last comments, questions, changes, or anything? All right, hearing none, all in favor, say aye. Any opposed? Any abstentions? All right, motion carries. Thank you. Next to our presentation, and I will let Cynthia introduce our speakers.
I'm really glad all of you came because one of the things we really want to do as a commission is provide information to residents of Charlestown so you know what's going on and you can make informed decisions. We're not here to tell you what to do or how to do anything. We're just providing you with probably two of Rhode Island's foremost experts on the aquifer, groundwater, and movement in the aquifers. So hopefully we're going to learn as much as you tonight. And I'm really happy to welcome Dr. Tom Boving. He is, do you describe yourself as a hydrologist, Tom? Yeah. At the University of Rhode Island. He's a professor at URI, and he specializes in coastal erosion and environmental hydrogeology. So how water moves below the surface of the earth, right? Because I'm really ignorant about this, and I need to know more. Yeah. And with him tonight, bonus, is Dr. Mamoun Ismail from URI, also hydrologist and an expert in the flow of groundwater. And Allison McCann could not be with us tonight. She sent me an email this morning saying she had a personal thing. So, but we still scored with Dr. Ismail. I'm very glad you could come tonight. So please, gentlemen, it's all yours. And short presentation, and then it's all about your questions. So this is why we're doing that. So do not hold back or worry that you're talking too much or whatever. Just ask whatever you want to know. Thank you.
Thank you, everybody, for coming. Started short. The most. Oh, easy. All right. Hi, everybody on Zoom. Again, thanks for inviting me. Thank you for coming this afternoon. I'm always interested to talk about water. I'm a hydrogeologist, and like I said earlier, I have a short presentation prepared, just going over some general concepts which make it a little bit easier to understand what we are doing at URI. And so if we can have the presentation going, there we go. So Charlestown, right there where the water meets the ocean, that's important for many reasons, right? I mean, we all love our beaches. We all love to be where we are in this very beautiful part of the country. And so it's important that we think about what the future holds for us, what's going on. Just briefly, I don't have to repeat much of it. I'm from Germany originally. You can probably tell from my accent. I'm a resident of Hope Valley, Richmond, for 23 years on Switch Road, and this is our favorite part of the state, so we spend a lot of time here in Charlestown on the beach. I've got my PhD from Arizona, in Tucson, lived there, moved here, again, 23 years ago. I've been with the Department of Hydrology and the Department of Environmental Engineering for those 23 years. I work in contaminant hydrology, the water, the science of water, and like you correctly said, how does water move? And more important, how contaminants move with the water. So it's a very complicated system because groundwater is what we can't see. It happens all beneath our feet. And most of us have a difficult time to envision how water moves below our feet, right? I mean, there's rock, there's soil, sand, whatnot, yet the water finds its way. And if the water is polluted, the pollutants find their way with the water. And what happens here, ends up there. And the question is, how long does it take to get from A to B? And as a hydrologist, we were using a lot of techniques, including modeling, where Mamoon will be talking about, or you can ask him questions later, where we use sophisticated mathematical models to help us better understand what is really a very complex system. Next one, please. So again, I don't want to make it too broad. I can talk all day if you want me to. That's what I get paid for at URI. So I limit myself to these topics here. Freshwater. Charlestown, most of us rely on wells. That's our single source of fresh water, and it is groundwater. More people move to coastal areas. What are the consequences of that? Year-round versus seasonal occupancy, right? Tourism. Then water quality. How does all these activities in this very narrow strip of land affect the water quality? Are there habits of ours we may want to think over new technologies, maybe in the light of emerging contaminants, in light of PFAS. Everybody talks about PFAS. I'm more than happy to talk about PFAS too if you don't know what PFAS are. And then saltwater intrusion. Is this an issue? Do we need to worry about saltwater intrusion in the light of climate change, in light of sea level rise, right? And more extreme events, more storms, more droughts, or I should say, more frequent droughts or more severe droughts. The same is true for precipitation. More severe precipitation events, maybe not more water in general, but much of it at the same time. Kind of the downpour we had a couple of days ago. Hurricane intensity and frequency will increase. Our water temperatures have been as warm as ever, and the trend is clearly upward. That's order, that's energy for more strong storms in the future. And fortunately, so far, we have dodged the bullet, but it may change. So we need to be prepared. And again, sea level rise, throw that in the mix, and we have a lot of things to talk about. Next one, please. And feel free to interrupt me, right? I mean, again, this is more a discussion I hope we have than me lecturing. But I wanted to give you some ideas what we're doing. And here are 3 slides from our South Coast research sites. There's East Beach, there's Blue Shutters down there. We have an inland site where the Rhode Island Water Resources Board has a well field. And then down on Matunic, we have another research site where we using wells, geophysical methods, observations to kind of better understand what's going on in this very critical area where the land meets the ocean. Next one, please. Just briefly, geology, it's important that we understand our geology here. Our area, as you all know, was heavily glaciated a couple 12, 15,000 years ago. There would have been a lot of ice outside. That's all gone. What's left behind are the sediments that those glaciers brought from far away and dumped right here, and actually dumped off the coast. If you go to Block Island, that's an end moraine. That's basically where the last glacier stopped and like a conveyor belt dumped a lot of material, which later became Block Island, particularly after the sea level rose because of all that melting ice, and the Block Island became an island. But our geology is not that much different. And in the lower part of that picture, you see the major units. There's a lot of sand and gravel here, which makes excellent aquifers. This is where we get our most of our water from in the unconsolidated aquifers. Below is bedrock. Bedrock is fractured, has cracks, and in the cracks we also find water. And many of you may have a fractured bedrock well, which can be yielding a lot of water or no water at all, depending on if you're lucky enough to hit one of those fractures. If you miss a fracture, you go home dry. If you hit the fracture, you have water. And then also in the mix are what we call till. These are the deposits that the glaciers dumped immediately when melting. So the Charleston moraine is a very hummocky, hilly area, hills, Rhode Island hills, right? I mean, not mountains, hills. But it really pinpoints where the glacier took a break from retreating. So it went all the way to Block Island, and it started melting. And the climate probably got a little bit colder again. It stopped for a while in Charlestown and dumped for many, many hundreds of years, maybe. And then it started receding even more farther north. And there's another of these episodes. So there are more other moraines farther north. But for us and here now, the Charleston moraine is important because it clearly defines the coastal area from, let's call it the hinterland. All right, so that's our geology. So superficial geology, heavily imprinted by glaciers. The bedrock has been there for hundreds of millions of years, but also is sculptured because of the glacial work that the glacier, basically like a gigantic piece of sandpaper, has polished the rock, has created valleys and impressions, and these are now filled with those sediments you're seeing here. All right, any questions about the geology? It's geology in 2 minutes. Okay, next slide. Oh, there we go. That's the very future. Yeah. Yeah, so there we go. So I just wanted to briefly talk about saltwater intrusion into coastal aquifers. Again, just highlighting some of the major processes here. So the upper of the two pictures, you see the conditions before development has taken place. In the coastal zone, we find, no problem. In the coastal zone, we find an area where saltwater sits below freshwater. Why is that? Why is saltwater below freshwater? It's denser, right? Saltwater is denser. So if you can go at home and prepare two solutions, one freshwater, one saltwater, put a couple of tablespoons of salt in a jar, stir it around, maybe add a little bit of food coloring, put it in the jar, and then slowly, carefully on top of the salt water, you add fresh water. And if you do it slowly enough, the two won't mix. And they will be sitting there for a while at least. The colored fresh salt water at the bottom and the fresh water on the top. Same is happening in Mother Nature. So in our coastal areas, we have fresh water floating on top of salt water. And that's a very fragile equilibrium because the density difference between salt and freshwater is not all that great. So a little bit of a disturbance and be creating mixing, and saltwater mixing with freshwater creates more saltwater, right? I mean, it's what it is because the ocean is so highly salted that just a little bit of saltwater turns freshwater into water you can't drink anymore. And in between those two zones, the saltwater at the bottom, the freshwater on the top, is a diffusion zone, we call it. It's basically a mixing zone where the fresh and saltwater are mixing together. Not super important, I just pointed out because it's in the picture. Now, when people start pumping freshwater, they're removing water from the subsurface. They're draining the pore space. And that pore space gets filled again. There's no such thing as a void or vacuum, right? A vacuum gets filled in immediately by salt water. So the second lower slide shows what happens when a well gets pumped. We basically creating a cone of depression in the surface of the fresh water as the result of pumping. You're also causing the salt water to come closer to the surface, closer to the well. And if we overdo it, salt water will be pumped from that well, and you basically have a failed well. It has become, the water is unfit for human consumption. Chloride levels, sodium levels. It's basically spaghetti water you're pumping. Yes?
How close do you have to be to the pumps?
Yeah, right. That's the $1 million question. And it varies strongly based on the geology, meaning some sediments are more permeable, conductive. They yield more water. So therefore, we can pump more water without creating such a deep cone of depression or forcing the water up. So sand and gravel is safer than, let's say, finer sand, silty material. If a well is completed in that material, much more easy to contaminate a well with salt water. In general, it is, as indicated in the slide that's no longer there, that mixing interface, saltwater, freshwater, goes inland and becomes deeper and deeper and deeper. It's actually less deep than indicated in that slide over there. So we're finding, and I show you a slide later to answer your question, saltwater even a couple hundred, it's 1,000 feet inland easily. And thousands of feet, yeah, couple, yeah. Mm-hmm. Right. Yeah. You're on Zoom.
I need to repeat that. I heard anecdotally that there is a well that's actually quite a bit inland, even further than 1,000 feet away from the coast, that has had saltwater intrusion in it, which really shocked me.
I show you a picture in a minute. You're absolutely right. I mean, it's tricky. And in some places of the world, 1 second, I'm working in India also. We found saltwater 2 miles away from the ocean at a fairly shallow depth of like 40 meters. Yeah, it's not unheard of to have saltwater encroach deep and deeper into the hinterland, into the terrestrial area. There was a question.
Once a well has failed, that's hard to say, is it gone for, can it be recovered again?
That's another very good question. It will recover, but it takes time. So let's think about how did the freshwater lens that I just described form. It forms because of precipitation. That's the recharge for our aquifers. What we're pumping out has to come replenished by the precipitation. So if you stop pumping and let nature do its thing, the freshwater lens will grow again and eventually will dilute the salt to the level where you can drink it again. But that takes time. And it's not like happening in a couple of days. So we're talking possibly years, maybe decades, depending on the degree of pumping that has caused the problem in the first place. So for all intents and purposes, you won't have water for a foreseeable future. Yes.
So is there a way to test your well?
Okay.
Is there a way to test your well to see what the depth is of salt water?
Yes. Maybe we go. So can we go back to the presentation? There we go. So the next slide, and then I think after that, I will get back to your question because, okay. So I was explaining to you saltwater intrusion. Often you hear inundation. So here in the coastal area, we can potentially see storm surge, overwash, and we call that inundation, where it is plausible that during a stronger hurricane, the coastal area gets flooded. That's saltwater. So that saltwater will infiltrate into the underlying groundwater, and it can totally turn the freshwater into saltwater with unknown duration. I can't tell you if this disruption will be over in a year, possibly, but can take longer. There's studies from the tsunami in 2004 where many coastal areas around the world got flooded by the overwash, and it didn't matter if it was a hurricane or tsunami. We were pretty safe here when it comes to tsunamis. I'm not saying we shouldn't worry about that, but it took in some places several years for the fresh water to come back. So that we call inundation. That's directly related to storm surge and hurricanes, nor'easter, that would also appear in the summer. Next slide, please. And this graph shows you several things. But the main intent is to show you that the saltwater intrusion is actually naturally happening. It's a seasonal phenomenon. So what we measured here is in a well near Blue Shutters, actually, right on the Blue Shutters parking lot, where we lowered a electric conductivity meter. Electric conductivity meter is a measuring device that tells us how much salt is in the water. Pure water is basically non-conducting, a very bad conductor. So we're getting very low readings, meaning fresh water, the low readings. But as the salt concentration increases, the electric conductivity goes up. And that's what these lines show us for winter, spring, summer, and fall. And on the top, on the x-axis, we have a measure of electric conductivity. It doesn't matter what those numbers mean, but towards the right becomes more salty, towards the left, less salty. Fresh water to the left, salt water to the right. Okay? And at the y-axis, we have depth. That's basically our well. So we're going down deeper into the well from the surface, down, about, what is that, 40, 20 meters, 16 meters? So 40, 50 feet. 50 feet. From the surface, we go down. Maybe I screen down. Let's see. So I'm pointing at let's see. So near the surface, very low, really stretchy. Oh, not even. Okay. So as we go deeper down into our well, the fresh water remains fresh until we're hitting this dashed line here. This is the sand and gravel overburden. This is the bedrock. That's the line between the bedrock. And once we hit the bedrock in this particular well, look at that. The hydraulic conductivity sharply increases, meaning we're hitting saltwater. And Blue Shutters, as you know, it's very close to the ocean. I mean, it's basically in spitting distance. So at that level, we're hitting that saltwater lens right there. So we're using a very simple device. It's basically a cable through which we send electricity, and the electricity is measured at the surface. If it's low electric conductivity, we're getting low readings. Once we hit the saltwater, the electricity goes way up, and we're getting high readings, and we know we have salt water or brackish water, whatever you want to call it. Now, we're finding that the lines, and we have 4 of them, seasons change. And the one in the fall stands out. See that? Means in the beginning, near the surface, we have already very high saltwater concentration. It's all relative, right? The water is still pretty okay, but it's definitely higher, much higher than in the rest of the year. So fall, when is that? That's at the end of the tourist season, end of the summer. We just pumped a lot of water from the aquifer, right? And the vegetation does its thing, the evaporation sucks a lot of water from the ground. So a lot of demand for water, and that's what we're seeing here. So nature is responding to that by filling what we withdrew from the aquifer with a fraction of salt water. And then as winter comes, goes the other way again, because now less demand for water, vegetation shuts down, maybe increase in precipitation. So we're seeing a dilution back to normal as in low concentration of salt. And then it starts over again next year. I have actually, that's what we're trying to figure out. This is very important, right? Is if over the years we're seeing a trend towards higher salt concentrations and longer time, or maybe it doesn't even return to the ideal conditions, we have a problem. Because that's basically the canary in the coal mine. If we're seeing these electric conductivity measurements go up and don't go back down, that's not a trend we like to see.
Recent studies been done showing this as a trend, or have they not been done yet, or are they?
We're working, in addition to South Coast and Little Compton area, on exactly this issue. And for the last 4 years, we have collected data showing that there are trends, and they're directly related to what's going on the surface. So in 2021, we had a drought. Was it 21? Doesn't matter. Last year it was exactly. That was directly, we could directly pick up the lack of water coming into the aquifer in the electric conductivity and the salinity in the aquifer in Little Compton. This year it's pretty wet. We don't see quite the same levels of salinity. All right. So in other words, it's very strongly dependent on what's going on at the surface. So over the longer trend, if we get less precipitation, we should see an increase in salt concentration. But then superimposed on that is the amount of water we people pump. And the more people live in coastal area, more pumping happens. That will amplify the effect of what I just talked about here.
With comparing Little Compton to, for example, Blue Shutters, Little Compton is not heavily developed area. And is where your well is located, is that in an area that is, for example, as public as the Blue Shutters?
We have several, 16 wells. We got very lucky in that the people of the town volunteered either abandoned wells or let us take some of that tap water to measure the electric conductivity. So it's not just one well that we're sampling, but we're finding that some areas are much, much more affected than others. And in one particular area of Little Compton, the reading's getting to the point where that well can no longer be used. It's a heavy user.
Is it a developed area right there where that well is?
Yeah, it's a developed area. And a lot of water being extracted very close to the coast. Okay, next one. So I mentioned we do use geophysical measurements, electric resistivity and passive seismicity. I'm not going into details how that works, but it allows us to peek into the underground, basically an X-ray of the near surface and what's happening there over time. And what you see here are 3 snapshots from 2019 through 2021. And we are on East Beach. East Beach parking lot, you see this up there, and then down to the south, the coast. So 200 meters, 600 feet between the ocean on the one side and the pond on the other side. So what we're seeing is blue is fresh water, red is salt water. And you see that the blue is floating on top of the red, meaning fresh water floating on top of the salt water, as expected. But over the 3 slides you're seeing here, let's wait for 2019, there it is. it's fairly wide, the blue area. Then it shrinks to a very small area in fall, and then expands again the next year in spring. It's kind of like inhaling, exhaling. The lens of fresh water becomes larger in the winter, shrinks in the summer, fall, large again, in, out, in, out. So this is this is natural because not too many people in that immediate area of East Beach pumping. The next pumping well is quite far away. So this is naturally occurring.
Daniel Urish in his report on you're probably familiar with.
Oh, yeah.
He's still alive, by the way. He's in his 90s.
Oh, wonderful. Yeah. Yeah.
He claims that 5 to 6 months of the year we're taking water out, and 7 months of the year we're building water up, and it's related to population in the summertime.
Yeah, I would agree with that. However, we have to revisit this in general terms because until recently, COVID, we had a very seasonal population.
Right.
Now have seen an influx of year-rounders. It means there's more water being consumed year-round than it was before. So maybe it's no longer 6 or 7 months, something like that, more like 3 versus 9. That takes away from the total amount. It's like a bathtub, right? If you fill the bathtub at the same rate as you drain it, the water level in the bathtub remains stable. If you take out more water than comes into the bathtub, guess what? The bathtub will drain eventually, be falling dry. So that's the game we're playing here. We have to be careful not to take out more than is being recharged naturally.
Who knows? You know.
No, that's why I'm so happy to share some of what we're doing. I mean, this was just published by my former PhD student, Jeevan Panti. Some of you have met him in November last year. In Mamoon, too, you're seeing something very similar. This is cutting edge information, and I'm happy to share that with you because it is difficult to visualize what's going on in the subsurface. And illustrations that are based in data, like this one, maybe help you to understand that our natural system is not static. It's very dynamic, and it can easily be disturbed. It will find its new equilibrium, but that new equilibrium may no longer support us who caused the disturbance in the first place. So anyway, I wanted to share that with you because it shows clearly the shrinking and expanding of the freshwater lens depending on the time of the year. Again, this is for the barrier island, but in the immediate coast, it's similar, very similar. Next one, please. So besides water quantity, so how much water do we have? We're also looking at water quality. Is that water fit for drinking? And we have records from about 180 sampling points, which is only a small fraction of all the wells in the town, right? We would love to have more wells. There are some areas, as you can clearly see, where there are big white areas where we have no idea what's going on. And some of these water quality parameters include bacteria, E. coli, fecal coliform, and so on, nitrate, salt, as in chloride and sodium. And we plotting this data and then extrapolate from what we know to other areas where we don't know. So in the next slide, please. You're seeing some of the data that we have prepared about 5 years ago. So there's some lag here because we haven't really updated the data. But the good news is there's a lot of green there. Green is good. But if you look carefully, there's some areas that are yellow and red. And these may be singularities because we only have one set of data. It could be it's a seasonal thing, maybe, could be many things, but we see areas that are clearly red. That's where the water is borderline or already beyond saltiness, meaning too much pumping, too close to the ocean, too much pumping. So the left is TDS, which means total dissolved solids. It's a measure for all the salts, not just for chloride, but sulfate and nitrate and whatnot. And the map to the right is chloride. So in terms of TDS, the picture is a little bit more dire than for the chloride. But again, we are seeing some areas right near the coast where the chloride increases. And just for reference, 250 milligrams of chloride in 1 liter of water, and you're seeing problems with your water supply system, corrosion, and all that good stuff that costs a lot of money to fix. We don't want to get to the point of 250 milligrams per liter. In some areas, we're already exceeding it. Again, only one data point, one time. What we really need is more data. And as somebody asked, what's happening in the future? We can only tell by looking back and projecting from what we know to what may happen in the future. So we really would like to have a few wells, we could call them guardian wells, where we come back again and again and again, and we don't necessarily have to send somebody out. It's actually very inexpensive. If we have a well, we just put in a logger. It's an electronic recording device that we can program to take a reading every hour, every 5 minutes, every other day, but whatever we want. Leave it there for 3 months, a year, come back with the computer, read it out, and we get a nice data set.
So to follow up with your question, we have a great audience today and we're all on wells. Is there an opportunity for residents to be part of this study? And next question is, how do we get in contact with you if there is interest in this group here to help with the study and to help learn more?
That would be amazing if we could form a group of people that share our concern or just our curiosity about what is going on. And what it would take is access. That's the main thing. And our students always look for a project like this one, where they go out in the field, maybe monthly, unless we have these electronic logger devices, which was about $1,500. And again, it would be an excellent master's project. And over time, we're building an information base, hopefully getting more people interested, spreading out. We get a much better picture of what's going on. And like I said, that's how we have been doing it in Little Compton for 3-4 years.
I was just going to say that. And maybe the commission could help out with gathering names and stuff and putting out. One of the things we've talked a lot about is with our meetings, we're having more guest speakers to help educate the residents and the public and whatnot. And we're looking to do more outreach. And that may be a great way to kind of reach out to the population. And if there's interest, we could gather those names and get them for you.
Yeah, and if there's any,
Send the clipboard around right now.
Right, he's going to do that.
We can do that. Yep.
Some of the data that you have, it's a little older. Ann Vieger had a study that was quite comprehensive in, I guess, maybe it was just in Quanticontog, I'm not sure. So it was just more site-specific.
yeah.
And at
Yeah,
this
Dr.
point,
Vieger,
that's what, 8-10 years old now?
Probably even older. And
Showing my
unfortunately,
age.
unfortunately for us, she's now vice provost for research at URI and doesn't do too much field work anymore. But when she was active, as you said, she was very active in the Coney area and collected a lot of information, painting a similar picture for this particular area. So yeah, if we can spread out into areas that are maybe even more densely populated, less densely populated, we will be more in a position to project what's happening in the entire Charleston area. But yeah, that could be a blueprint for a study that I just described. No. Okay, there's. I don't know, anybody been to Yucatan? There are these cenotes, right? So we're talking karst. Karst is limestone. Limestone is heavily dissolved. There are truly caves down there flooded with fresh water. And in this particular instance, we actually have fresh water sometimes dumping right into the ocean off the coast, far off the coast. That's an exceptional environment. You don't see that here. There's some debate, but I've not seen any data that suggests we have a major groundwater discharge off the coast. It's maybe diffuse, but that's just what it is.
I would think that at the bottom of the ocean, it's silt, it's dirt, it's sand, whatever it is, and that the weight of the salt water, it would diffuse and maybe eventually filter itself out, kind of the way a septic system works.
Oh, that would be wonderful. Because that's, unfortunately, once we have salt in the water, it is very difficult to get it out. And basically, two ways. You can distill the water, right? That's what rain is, distilled sea ocean water. Or you use reverse osmosis filters. And these filters are in actually great demand because this is really the only practical way right now to create fresh water from salt water. But they're very energy intensive. It's a solution, again, restricted to places where money is available to invest in desalination. And when we talk desalination plants, we're talking reverse osmosis plants. Yeah?
Other than the volume of pumping, does the frequency or number of wells, as well as the density, also have an impact on the quality of water and the saltwater version?
Absolutely, it's additive. So I don't know if you remember in my slide, saltwater intrusion, I was talking about the cone of depression that forms around the well. This is basically the three-dimensional, think about a funnel, where the well is in the center, and the area surrounding the well is influenced by the pumping because you're draining water from the pore space, pumping it to the surface. So if I had my computer here, I could show you a simulation that if you put two wells next to each other, close enough, the cone of depression will overlap and causing in the center, they overlap, a much larger drawdown. So if you multiply that by many wells, too close together, you see a regional drop of the water table. And that has also implications for the septic systems. Yeah, a can of worms.
Oh, God.
Wonderful. Please participate. And if you're concerned about your data, we keep it anonymous. We will not disclose the name of the well and like that. This is understood because we also honor your privacy. And in fact, we would like to hear from the anecdotal well that you mentioned places where there are problems, where are the salt concentration already so high. I know that's not what people like to talk about. That's why I'm saying we keep it anonymous, but that would really help us. So any participants, please sign up. And we will be in contact. We probably follow up with an email and maybe a visit. Sometimes, okay, there's one thing. If you're, let's say, if we can't have direct access to the well, which is standard. I mean, these wells are capped and we don't want to disturb them. There's concern for contamination. We don't want to do that. So what we usually do, we come with a bottle and take after running the water for some time from your tap, a sample of water, a liter, and then take it to a lab. However, if your home has water treatment system, then maybe there's a faucet before the system we can use. I'm just throwing this out because that would screw things up, of course.
So explain the benefit of doing that to someone that's not here. Some have newsletters, whatever. We could like do a commercial. Could you just give us a couple of sentences and we could let people know how to, we could also get that from you another point if you'd rather.
Yeah, we already prepared a short statement explaining what we're doing, why we're doing it, how we're doing it. And I'm more than happy to share that with you. Just send me an email. I can. Wonderful. Yeah, that would be tremendous because that's really what we don't have is enough data. Science flourishes with data and withers in the absence of data. And the more data we have, the more confident we can be in our projections. And maybe things are not bad. I'm not telling doomsday is coming, but it's not. These processes are slow, gradual, at least they have been in the past. And the earlier we catch a trend, the earlier we can respond to it. And the earlier we catch it, the least painful it is. Right? I mean, if we identify a problem, we can discuss solutions. Like, I don't want to go into detail, but there are ways to address what we thinking is happening. Yeah. I'm German. I would support beer. Beer. Yes.
I'll re-ask the question. Could you give us some general ideas on what we could do to address the problems?
Yeah. Let's look west to places like California, Arizona, Nevada, and see what they're doing. They're already in a position where they have very little choice. They're forced to make major changes. Means in Arizona, when I was there during my PhD, they paid you money to switch lawn from heavy water consuming plants to what is more appropriate to the climate in the desert. So instead of wasting our water on irrigation, let's think about sustainable gardening, for example. Pools, do they really have to be refilled every other day? I'm exaggerating, right? It comes down to making choices when you buy household appliances. Go for the ones that save the most water, that need the least amount of water to complete a dishwasher or a laundry cycle. There are choices we can make, small choices, but they're additive. And so there are many things we can do easily without really changing our lifestyle dramatically. If that doesn't help, then we need to think along more rigorous changes that may require water use restrictions. We're already seeing them advertised during some parts of the summer, right? They could become more restrictive. I don't want to go as far as limiting development in the coastal area, but that may also be necessary. We only have a carrying capacity, and when we exceed that, everybody's in the same boat at that point. We all suffer. So if we overbuild or extract, that can be one way to encounter the problem, to just think smartly about development. I'm not anti-development. I clearly want to make that clear, but there are smart ways to do it and there are not so smart ways.
To follow up on that, have you seen any good examples of stormwater retention and recharge in small scale sort of communities having a big impact? The question is if there are any measures around stormwater retention and recharge in more community areas and small scale that have an impact.
Yeah, right. So remember, rainwater is our recharger of groundwater. So if we seal the surfaces by parking lots, by buildings, by structures, and whatnot, we making it harder for the groundwater to receive the beneficial recharge from the surface because the surfaces are sealed. Instead, the water is being routed to the next stormwater drain, put out in the ocean to quickly become salt water. It's of no use. So in some parts of the country, we're already seeing this issue of surface water, sealed surfaces and the impact on the groundwater. So what we want to do is keep our soils open, minimize impervious surfaces. Like a parking lot could be built by permeable structures, permeable pavement, special type of rocks. I'm not an engineer of parking lots, but I've seen many examples where we enable the rainwater to reach our groundwater. Also, retention ponds, you mentioned. Retention ponds are structures where we capture the rainwater before it flows in the ocean. And it gives and allow the rainwater to seep into the subsurface in this retention pond area. So think about it as a temporary lake. Then the water goes away because it seeps into the groundwater, replenishes it, and we have banked more water for the season. If we don't do that, then the water gets lost in the ocean via storm drains and these engineered systems that get rid of the stormwater quite quickly for good reasons. So we don't want road flooding. We don't want surface or basement to flood. So retention ponds can be constructed, but they have to be constructed in areas that keeps it away from problem areas. And there are whole books written about, whole classes are being offered just on the subject of designing stormwater structures. And there's a very good, actually, Rhode Island for a while was a leader in stormwater structures, best management practices. And 2010, I think, was when the Rhode Island Stormwater Report or manual was published. So if you go to the DEM website, it's available for free. It gives you some ideas about what you can do at home, like rain gardens, or what we can do at the municipal level. And yeah, it's a really good reference document. I can make that available or just download it from DEM's website.
Rain harvesting on rooftops. So in some other parts of the world, like they harvest rain from the rooftops during the rainy season. Similar way.
Yeah. Yeah, we just have to look to a place like Jordan where it doesn't rain that much and the rainwater is really, really important. We may want to learn very simple solutions, thousands of years old. We don't have to go high tech. All over the area, right? They really help, absolutely. They absolutely recharge the groundwater, and that's what the goal should be. The more we recharge, the better it is. They're too salty. That's the problem. That's the problem. In fact, if I think 3 more pictures or so. If you have some patience, I show you. Next slide, please. Next slide. We can talk about that later. There we go. We have a study going on where we fly drones over the salt pond areas, particularly right at the it's not the beach. What do you call that? Yeah, the cove, but right where the saltwater and the pond and the land meets. Yeah. But no, it's fine. So we're flying our drone right over the coastline, so to speak, and this is a salt pond, so it's not really the coast, but so what we're doing is we have an infrared camera mounted on the drone, and the infrared camera picks up difference in temperature. Now, in the summer, the salt pond is warmer than the groundwater. So when groundwater seeps into the salt pond, we can find it because we are seeing these darker blue temperatures, meaning there is fresh water discharging into the pond right there. So this graph shows how the temperature of surface water, groundwater changes over the year. So there are 2 times in a year that this works best. That's late in the fall and early in the spring. So very simple way by drones, taking snapshots of the coastline, we find where groundwater mixes with salt water. As you can see, these are only, I think this is a little boat here. So this is the scale we're talking about. It's not a huge plume, but you can clearly see there's an inflow of fresh water into the salt pond. And what was the question? Sorry, who asked the question? I think the question was about the salt ponds, yeah. So the salt ponds, unfortunately, they're salty. And the fact is, we actually have flow of groundwater into the salt pond, and thank God, not the other way around. That would be bad news, and that brings us back to the saltwater intrusion, because the salt ponds are salty, and the same what I said is true for the immediate coastline is also true for the salt ponds. So if we pump too much along the salt pond, we're ending up with a situation we don't want. So this is good. Are we going to keep it that way?
Bill Farmers used to say that we were able to raise oysters in salt pond area because it had more fresh water coming into the salt pond years ago, which is not true now because there's very little natural growth in the oyster population, only what people put in there.
Yeah.
So that may be historical.
There's, right?
Evidence.
I mean, we're taking out a lot of water. No, we're putting a lot of water back into our system. So our house is relying on septic systems. So we have a well, we're pumping out the water, we use it, and then it goes out the other end into a septic field. That's where the used water is recharged to the groundwater, which is a great thing, right? So we're really not consuming all the water we're pumping. Only a fraction of it gets lost in the process. But when we recharge our groundwater with septic water, we also bring in a bunch of chemicals, bacteria, nutrients, and they flow with the groundwater to the salt ponds. So the decrease in the oyster population is probably not just affected by less freshwater, but also by what is in the freshwater. That freshwater is not so fresh anymore.
Temperature plays a big role in that, particularly with the oysters. Temperature has risen up. And back when I was working with Marta Gomez-Giari, we started to find dermo and MSX disease, which is pretty much what's wiped out our oyster resource.
Yikes. Yeah. The system is in a state of change, right? I mean, I was saying earlier, the Mother Nature will find a new equilibrium. There may not be the same ecosystem that we used to, will be replaced by another one that's more tolerant towards higher temperatures. I don't want to go too far off the subject, and I'm not really an expert, but I think we have an increase in blue crab moving into our area, displacing the lobsters. Lobsters go farther north because the waters become warmer, and people are already thinking about new recipes for blue crab, commercializing it, right? I mean, that's what I heard anecdotally is coming towards us, and lobsters go north. So the same may be true, that the type of oysters that we used to will be replaced by more heat tolerant or warm water oysters. But again, I'm not an expert on that by far. But let me go back to the previous slide. So I was mentioning septic systems being possibly the source of pollution. I shouldn't say possibly, but it is a source of pollution. We know that because some of our septic systems fail. They're old, they weren't designed for either the use they're experiencing now, or sometimes has also to do with the fact that the distance between the septic system and the groundwater table is becoming smaller. Sea level rise. Think about what happens when the sea level rises. It rises the groundwater table because the groundwater floats on top of the fresh water, so the salt water. So if the sea level rises, so does the groundwater. And the distance between the bottom of the septic tank and the groundwater table has to be at least 3 feet, roughly, for the system to be effective. That's cut to 2 feet, to 1 feet. Septic systems don't work anymore, they fail. So thinking about the future, we really need to take into account what would our area look like if the sea level is up by 30 centimeters, 1 foot. And that's not too far in our future. I mean, was it the Financial Times yesterday, I believe, headline, first page, and that's the Financial Times, it's not some crazy journal, right? Talking about much larger, much quicker melting of glaciers than we have anticipated. It's accelerating to a degree where these worst case scenarios all of a sudden don't look like worst case anymore, more like that's what's coming. Meaning in our lifetime, we can see sea level that's much higher than it is right now. Definitely in the lifetime of our children. And we should be smart enough to think forward 30 years from now. It's not so far away, right? 30 years. It sounds like that happens quick and all of a sudden, yeah. Anyway, that's more philosophical, but we really need to take a long-term view here because these changes are happening. And they're happening with us or without us. And they will displace us if we're not finding ways how to address what's happening.
So what's this about?
Yeah, what's this about?
Sugar?
Yes. So sucralose is an artificial sweetener, which turns out to be very resilient, meaning resistant, recalcitrant. It doesn't degrade rapidly. So we're using it as a tracer because sucralose is in so many products, right? So once it enters a septic system, so let's start at the very beginning. You drink a Coke or some drink that has sucralose in there. Some of it gets digested in your body. Most of it makes it right through, and you go to the bathroom, you inject it into your septic system. In the septic system, it doesn't break down, goes right into the groundwater, and lo and behold, it will show up in the coastal waters, in the salt ponds, via those blue discharge points that I pointed out, right? And we can pick it up, we can measure it. We can measure sucralose in those waters as shown here. All these blue dots are sampling points where we're finding sucralose. And it's basically everywhere. And we're using sucralose as a proxy, a tracer to basically establish an area being affected by septic effluent. Because there's no natural source for sucralose. Now what we're trying to do is to correlate sucralose to PFAS. And PFAS are per and polyfluorinated alkylated substances. That's a mouthful. They're basically compounds, long hydrocarbons with a lot of fluorine attached that makes them super stable. They don't break down naturally. They're not natural in the first place. So when you find them, you know, you have water impacted by people, by us. And all of us use some sort of PFAS. Let it be Gore-Tex, let it be, I don't know if you eat microwave popcorn, the waxy interior of the bag. PFAS are great because they keep the grease in the pocket. So when you shove that popcorn back in the microwave, it doesn't result in a lake of grease after you're done. But yeah, Teflon pans, so many products. So you don't have to be an industrial user of PFAS. Even households are source of PFAS. And we're talking, we can now pick up these compounds at parts per trillion. What does that mean, parts per trillion? So if I have, the threshold is 2 parts per trillion PFAS. If I find them, and the water is considered impacted. Think about a room filled with 1 million ping pong balls. 1 million ping pong balls. And then we paint 2 of them red. That would be parts per million. Parts per billion is a room filled with 1 billion ping pong balls. 2 are red. Parts per trillion, that's 1 million times 1 million. Ping pong balls, 2 are red, and we can find them. That's how sensitive our instrumentation is now. Right? So, in other words, we're finding PFAS everywhere. Everywhere in Rhode Island, everywhere in the world, in the Arctic. If you would volunteer blood, I would say 90% of us, maybe even 99%, will find it in your blood. It's out there. The effect of PFAS still debated, but there's plenty of evidence that it interrupts the neurosystem, can have cancer, can cause cancer, can have all kinds of effects. But honestly, I'm more concerned. PFAS is bad enough. But think about medication now. All of us take medication, right? About, in the best case, I would say 40–50% of the medication get actually used inside the body to do whatever the medication is for. An aspirin, right? You're taking a headache. The rest of the aspirin, the remaining 50–60%, goes out when you go to the bathroom. Back in the septic system, back in the groundwater. Aspirin is probably the least worrisome pharmaceutical we can think about, but there's lithium, there's Prozac, there are antibiotics. They do the same thing. They get through the body, into the septic system, into the groundwater, and very little is known about these emerging contaminants. What do they do? There's evidence that there are bacteria that become resistant to antimicrobial compounds, pharmaceuticals. They simply don't work anymore because the bacteria are exposed in the environment to those compounds. Next time you go to the doctor and you caught a antimicrobial resistant bacteria infection, that particular set of pharmaceuticals will no longer help you. There's a big search right now for new antimicrobial medications because we're slowly running out of tools to fight infections. And I just spent 4 months in India on a Fulbright in testing river water in India. And, oh boy, yeah. It is, it is crazy. We're finding in some rivers antimicrobial concentration of, let's say, trimethopentherine that are in the range of what a doctor would prescribe. So in other words, if you drink that water, you could theoretically save yourself a trip to the doctor. You probably die because there's so much more stuff. And in those rivers are bacteria that are already resistant to these pharmaceuticals. So that's one thing. And then there's just no fun drinking water that's laced with neighbor's, whatever medication. So. Oh, we can have a field trial. Yeah, right. I mean, the other studies, an interesting one that I mentioned to my students in Italy, the Po River is in the northern part of Italy, all the way from the Alps down, and then discharges near Parma, if I'm not mixing up my geography here. But along its way, it flows through major residential urban cities. And water samples were sent to the lab, and they picked up cocaine in huge amounts. They calculated backwards from the concentration measured in the water how much cocaine must have been consumed along the Po River, and it was horrendous amounts, thousands of kilograms. Right? Yeah. Hopefully you're not there.
Can you tell us how well
Yeah.
presentation
No, not at all. And it goes kind of along the question earlier. If I had anticipated your question, I could have shown a very intuitive, simple simulation showing that indeed one well, if too close to another well, impacts neighbor's well. In many ways, we can see this in the worst case. Let's say your neighbor has a deep well and you have a shallow well. If the neighbor pumps a lot of water, your well will run dry, worst case, because the water level, we want the water table at least as high as our well is, right? So our pump has to be in the water. So if the water level drops because your neighbor pumps like crazy, your well is dry. So what are you going to do?
That's my question.
Yeah.
What can you do, if anything?
Yeah, so most people would say, okay, I have to drill a new well. And then they drill a new well, which is deeper than neighbor's well. You know where I'm going? Yeah, that's the tragedy of the commons. We're sharing what is one resource, the aquifer, with everybody on top of the surface. If we don't get our act together and we have some bad players, the entire community will suffer because it's one shared resource.
A little while ago, you mentioned about Rhode Island being kind of a leader with stormwater management, but you didn't say that we still are. I realize that that's statewide, and I'm not sure how that works into our rural community because we don't have some of the same systems. But I'm curious, and I just want to mention one other thing, a report I heard on the radio this week of a community in Arizona, a rural community that had a large agrarian farm that was drawing basically all the water, and their wells were going dry, which is illustrating, I think, some of what you're saying.
Yeah. So first, the reason why I said Rhode Island was a leader, we're still pretty good. We're still pretty good. But in 2010, we were right there on the forefront with the stormwater manual, and it's still really good.
What would you recommend to make it really good?
It needs to get updated for what we're seeing now, changing climate. Because many of these structures were designed for what was a 25-year storm, for example. A 25-year storm may now happen every 5 years. Or in the future, maybe, you know what I'm saying? The same amount of rain that we received every 25 years on average, we may see now every other year. Right? A 500-year flood may not happen another 500 years from now, but could happen more frequently. So when we design stormwater runoff systems, we base them on the long-term averages from the past. Looking forward, these long-term averages will be exceeded according to the climate projections. That's a slow process, but we need to revise our manuals accordingly. So it's a dynamic process. We can't just stay steady. About the Arizona example, you're absolutely right. There are areas in Arizona where water is being mined. It's called water mining. And that is what it is. Crazy amounts of water pumped for agriculture. Often what's happening, and there's a big uproar in Arizona about it, other countries own large tracts of land to produce alfalfa in the desert. Crazy, right? Pumping groundwater to produce alfalfa, very water consuming plant, but the groundwater is free, more or less free. So they have all the rights to the water, pumping like crazy. That alfalfa gets harvested, put on a boat and shipped to way far away. Crazy. In the process, the water table is lowered so that the old farming communities surrounding these areas run out of water. That's happening. There are water wars fought in the West. I mean, not with guns, but legal wars right now where it is about survival.
I have a couple questions about the well. I realize you're speaking in the generalized sense of the groundwater as a whole. If too many straws are in it, it begins to go down and one well's deeper. But there's also a lot more complexity behind that, where one well may be 100 feet and produce 30 gallons a minute, and another well that's 50 feet away or 200 feet away may be less deep, more deep, and produce half as much. So I just get nervous with some of the statement, where we get into the generalized, where everybody jumps into that and says, oh my God, now if we put 5 wells here, that's guaranteed we're dropping water, and that's the case. It's a lot more dependent upon the underlying.
Oh, you're absolutely right.
Correct.
You're right. I mean, I'm very much generalizing, but that doesn't take away from the fact that we have X amount of water. And if we pump out more than comes in, that's simple math, right? It's like a checking account. So yes, but we have to be very careful because geology is a tricky business. It changes quickly. You mentioned there could be a well that pumps 5 gallons. Next door, you pump 50 gallons. Sounds a lot like a fractured bedrock aquifer, meaning those deeper wells where we have to hit a fracture to get water. The fracture is big, we get a lot of water. Fracture is small, you get a little water. If you have no fracture, you don't get any water. For the superficial aquifers, the sand and gravel, I can be more general because the flow field is much more connected, more homogeneous. And what I describe can be extrapolated over quite an area.
That was my next question. With Charlestown, I mean, as much as it's very important to see our coastal part of it, but we look at Charlestown on our geological level, is it identical across the town, or are there actually a lot of changes in a small area from our shoreline into our northern section versus our east and west?
There are. But again, we have to first think about how do we define large changes, right? I mean, we're talking Rhode Island, so elevation change, yes, I described coastal area and the moraine, Charleston moraine and farther inland. That's typically taken as the boundary of our aquifer, and south of it is the aquifer that the moon is modeling. And for modeling purposes, we usually generalize over, what's your grid cell size roughly? Feet. So 200 by 200 feet is basically where we would say within that 200 by 200 feet, we're treating material as the same. Then the next cell can be slightly different, but again, 200 by 200 feet. So that gives you some idea about what we feel confident or reasonable to extrapolate. So 200 by 200 feet, that's an acre, right? And the changes between 1 acre and the next are most likely because there's a change in the geology from bedrock to unconsolidated sand and gravel. The depth of bedrock is also changeable, and there's another slide I have somewhere I can show you where we used seismic methods to map the interface between the bedrock and the material above. And we're seeing that the bedrock is going up and down and left and right, and we're getting more and more sophisticated with this new technology. And yeah, so it is very site specific, but again, in general, my assessment stands that we have a limited resource. We can only take out as much as comes in. How much that is depending on where we are in Charleston.
No, I just want to add, this is where comes the need of more data, more like testing. So we need more testing wells to know the hydroconductivity of the aquifer. And so we know how fast the water can flow, right? Then we'll give better answer for your question.
It seems like a lot of those data points you had are south of Route 1 and shoreline data points. And maybe there's a possibility of between the commission and the rest of the town where we can get you some more data points on the north side in those neighborhoods.
Yeah.
So you can really get a better picture of the town as a whole to see exactly what the differences are and where things are moving in different locations.
That would be wonderful, right? I mean, again, we feed off data. The more data, the better. Yeah. And yeah, again, I mean, like, we can talk probably another evening just about the geology of Charlestown and what we know, what we don't know. Like I said, the Charlestown moraine is often considered a boundary. It may not be a complete boundary. There may be buried, and again, now I'm talking details here, but the picture is much more complicated. And yeah, so there are gaps that we will love to fill, particularly towards the north of Route 1, which is also very important because some of the recharge, the water that you're drinking down here comes from there. So an important area.
There are those who are saying, who live south of Route 1, that only the water that comes from the sky and septics is the water that recharges the aquifer. But there's some people who have said, and I don't know if this is accurate, that we are getting water from north of the moraine, that it's coming through. Can you verify either one of those statements?
I'm not in a position to verify one or the other. And however, when we look at the topography of the bedrock, the glaciers left behind a sculptured bedrock where some places they carved out, eroded more materials than in other areas. So it's plausible that the main lobe of the glacier left behind would look like, if we remove everything on the top, like a valley, right? So, and if the moraines is sitting on top of such a valley, there's a good chance that maybe there's material beneath which is more permeable, kind of not a barrier for the water from the north to migrate to the south. It's plausible, but we don't have the data yet to confirm what we're suspecting may be happening. And then where is it happening? So, you know what I'm saying? Would that change the picture? A little bit, but only for that area that is immediately affected by this paleo channel. It would definitely help to know that there is a connection to the north. But I can't tell you that's indeed the case. So more data.
So
Do other people have questions for our water scientist?
Or any last thoughts from our side?
I was hoping maybe, I'm sorry, but I was hoping maybe one or both of you could just describe what you do know about our aquifer, the one we share, that is our sole source.
Yeah. Well, I think we are at a critical time where right now I haven't seen massive problems. You saw my data for the chloride and TDS in the water. Locally, there are spots where we should probably check around and find out if this is a growing problem. Overall, we are at the time where we can make the smart decisions. We have time to act, to anticipate, to collect more data, more evidence, to put our decisions that are necessary on solid grounds. If we don't do anything, we're leaving ourselves open to large vulnerabilities in the future. We could get lucky, nothing happens, but the indications are that we are at the critical time where Mother Nature is taking a look at what we have done to it. I mean, that's overdoing it, but we're definitely affecting the natural system, and we need to make sure we understand what we have done, what are the consequences, and can we remediate? Can we adjust? Is there resilience? Do we have to retreat? So these are all options on the table, and then that's why it's so important that we have these discussions. And I don't have the answers. I told you pretty much everything, not everything, but to the degree where I feel I can share with you what we have seen in the field based on data. And the data indicates natural phenomenon are at place, but we're also seeing anthropogenic issues. And these processes are slow, so was relative to our lifetime slow, but still fast enough to change our environment that our children will see a different Charlestown than we are used to. And I think that's the mindset we should think about, these changes that are coming, that are in progress. But we can't put them off anymore. We have to act now. And maybe it's not bad. I'm not a doomsday crier here. I'm just think it's very important that we think about where we are in the location right at the coast, in an area that's very popular, rightly so, where people desire to be and want to do all the good things that we're doing. Let's hope we can continue that. We just have to be smart about how we're doing it.
I think what you're saying is very important.
Oh, yeah. Please.
I think this is like a good opportunity for me to address the importance of data. When I started to do my model to simulate the groundwater flow in this area, in the whole watershed, I was actually surprised to find that we only have one monitoring well run by the USGS. And it's been monitored for maybe tens of years. And it's, the data is collected monthly. So what happened during the month, we didn't know. So just once a month. And then for the whole watershed, we have only one well to measure. How would I do, my study, right? So more data is really needed in this watershed. We are in the proximity of the ocean, so we need more data near the ocean. So more data about water level, and also more data about how much water is being pumped from the aquifer. Because models, they depend on data. We have a saying, sorry to say it, GO, garbage in, garbage out. So, I still can run a model, but do you trust it? Do you trust the results? it depends on the data and the quality of the data. So I hope to see like more efforts on data collection in this part of the world. Thank you.
I was just going to say, I'm glad we have some town council members here. And we, of course, have a commission here. But from what you have said, there are some policy implications and implications for work that we as a political body need to do looking forward. We can't put our heads in the sand anymore about these issues. They're right smack in front of us. And by not doing anything, we've made a decision. So one of the things I have been pushing for is that we need more study. We need to do more. And I think the town and all our commissions need to work together to encourage that. So that's just a.
Yeah, no, and you're really forward looking. I mean, again, we are here because of exactly what you said. We want to know more about, and we see reality, we're staring reality in the face. And yes, go ahead.
Yes, and Dr. Boving, if I may, just as one of those council members, there are 4 of us here in attendance, and this is something that the council is looking at. So we don't want to leave anybody with the impression, and we do have a very active Climate Resiliency Commission that has been doing a lot of work. So I also want to take a moment to acknowledge all the work that you all have done, and we appreciate it. So thank you.
Our
all right.
meetings are always open to everyone. So we,
Well, people aren't larger size than probably most. A lot of
third
people don't.
Thursday of every month at 5 p.m. here.
But other than attending a meeting, people need education. They think the water comes from the ocean. A lot of the people do. And we know that. So we all share in trying to help. What can we do and what are you doing to help educate?
As part of, so now our mission now is 1.5 years new. And a lot of the first 1.5 years, we've really been getting together with the experts and presenting this information. And we've been really overwhelmed that we have had support and we've had people come to the meetings to learn and to ask questions. And that's what we need. I mean, basically this topic, Dr. Bowman's back and he was here once before last fall. And he came back because this topic was such a big issue to the public. We have every meeting, we have a public communication. So any issue around climate change, resiliency, sustainability, that's what we're looking for. We don't want to just be a commission that goes and works in a silo. This is about the entire town, not just the coast, not just inland, the entire town. And we're trying to get the best information up there. And that's why we look to the experts to come in there and present that to the group. So again, as Cynthia said, all of our meetings are open. This is our biggest meeting so far, but we've also had others where we've had 15 people in the audience for a commission meeting where there's nothing controversial going on, just learning. So that's a really good thing. We want to see that. And we're going to be, in terms of the public education piece, we've been talking a lot about that, about potentially a website or something like that we can start communicating these things more. And then also looking to you all, because we can only do so much as a commission. We need help getting the messages out there too. So the stuff that you learn here, talk to your neighbors, find out more and come back to us with other issues that are of interest. So we'll get the right people here to discuss these topics.
And also we're open to ideas. You all have ideas for people you want to learn from at these kinds of things. We're open to that. I mean,
How about the town council setting some money aside to do some of these studies that we're talking about?
well,
There is-
learned about it now.
Right, but there is money in the budget for climate resilience. It's already there.
We're spending it on trees.
Hi, I'm Tina Spears. I'm your state representative. And I came tonight because this is obviously top of mind for all of you as well for myself. I Senator Gu is in the same camp as I. The town can't do it by themselves. You need state support, you need state funding. There needs to be more resilience planning. We are actively working with our South County representatives to try and make sure that you have the resources that you need to act, and hopefully working closely with URI, DEM. We literally just had a meeting this week, several representatives and myself, to discuss this very issue. So we know it's top of mind. We know it's coming. I did want to ask you one question from an infrastructure side of things. We talked about a lot of planning, things that we can do that are natural responses. Infrastructure, when we think about what's happening with our septics infiltrating into our grounds, do we need to think about municipal septic? Do we need to think about desalinization? Are those things that coastal communities have to consider when they're thinking about this?
Yeah, I think we would definitely talk about that because in a catastrophic event, it could be a hurricane, which has, hit the area before. We would have to have a plan B. A municipal water supply system would be something that could alleviate some of the problems we talked about earlier, the inundation and mixing saltwater, freshwater, which we talked about that. Very important. Desalinization plants, I don't think we're quite there yet. That may be something for the more distant future. But it's an option that should be considered, should be at least evaluated so that we have already the decisions made, the hard decisions. So when time comes, we don't have to reinvent the wheel or start the long-term process of getting to where we could be already. Septic system, wastewater treatment plants, I know they're not very popular because there's a huge cost connecting everybody with such a treatment system. It's a question that we have to at least consider, but it also takes a lot of education to make people understand why such systems are beneficial. Why do we talk about a centralized water treatment? Why do we talk about drinking water companies supplying water for all? Some people don't want it. Some people, I understand, are vehemently opposed to it. But at least we should have an educated audience, educated voters, ultimately, who can make decisions based on facts, on an understanding of what's going on. And this is not hard science. I mean, I'm not a brain surgeon. For me, it's pretty straightforward. And again, I'm more than happy to come back and continue this discussion. I love it. This is great. I think there's so much that we can discuss and together work towards what is a solution that is acceptable by the broad public.
No, I just want to clarify, I'm not advocating for any solution. I'm just simply asking the questions, like we have 30 years, right? We have 30 years to solve what we see as the biggest change in our topography, in our
It's good to start the discussion.
Yes.
Yes, exactly.
Thank you.
Wonderful.
All right, any last questions? All right, I want to thank our guests for coming in today and educating us all. And I want to thank you all again for coming to learn a little bit more. And again, feel free to reach out to any one of us. We are looking for additional topics and questions and concerns and whatnot. And if we can find the right people to come in here to discuss it, we hope we're the venue and the platform to do that. So thank you. If you want to stay for the rest of the meeting, you can, but if not, you can go. All right, I want to take a. Okay.